All right. So these are the Unit 1 questions or Unit 2 conceptual questions. Check your understanding questions. So question 1, we've got two walls made of the same material. One's thicker than the other, twice as thick as the other. And the relationship between the two thermal resistances are, well, this just goes to Ohm's analogy and looking at the equation, and you can see if it's thicker, right? And if it's twice as thick, the thermal resistance to conduction is going to be twice as big. Insulation on a circular pipe is shown for the same thickness and type of insulation. The thermal resistance of the insulation is, and the answer is lower for larger dimensional pipe diameter pipes. Oh my goodness, lower for larger diameter pipes. And so if you look at that equation for thermal resistance to conduction in a cylinder, and you look at the natural log of R2 over R1. So just take a pipe with a thickness of 2 inches. So, and if you compare the value of that natural log R2 over R1 for something that is 2 inches thick, but one has an outer diameter of 3 inches versus 22 inches, then you'll prove that to yourself. All right, a plane wall has a thermal energy generation per unit volume of Q, and that should really be Q dot, and heat flows out of the wall as shown. If T0, T at x equals 0 is greater than T at x equals L, the relationship between the two fluxes is. So this is the case of figure 3.10a, where you have this asymmetric boundary condition going on. And what you'll notice is that, remember the heat flux, it's related to the temperature gradient. And on the left-hand side uh, at x equals, well, in the figure 3.10, it's at x equals negative L. But on that left face, you can see that dt dx is smaller, right? The slope is it's not as steep as on the right face, right? And so the heat flux on the left-hand side will be less than the heat flux on the right-hand side, as is evidenced by what I'm showing you right here. Okay. All right, question 4. The mechanisms by which thermal energy is generated in a solid include all of the following except, and the answer is this one. So the key word here is generated, meaning that it's a positive term. And in this case, for an endothermic chemical reaction, the thermal energy would be consumed. All right, steady state temperature distribution in a plane wall is shown. Want to know about the heat flux, and heat goes in the direction of increase or of decreasing temperature, and so it's going to be a positive number. If we said that those temperatures were equal, so question 6, T1 and T2 would be equal, and so in that case, you don't have any heat transfer because there is no driving force, there's no temperature gradient. All right, question 7. So you got a plane wall, and 1, 2, 3, 4, those all show different temperature profiles. If the heat flux is positive in the direction shown and it's increased, steady state temperature distribution will change from, well, if it's positive, then, and you know that Q goes in the direction of decreasing temperature, then option 3 and 4, option C and B, it can't be it. It's either 1 or 2, right? So either A or B. So if that heat flux increases, that means the temperature gradient increased. The temperature difference between T1 and T2 increased, right? And so that would be the case for 2 to 1, right? That temperature gradient increased. The line got steeper. Question 8, really the same question. Again, the heat flux is positive, so only A and B are possibilities. And since your temperature gradient, since your heat flux has decreased, that means your temperature gradient has to have decreased, and so it's going from 1 to 2. Steady state temperature distributions for the same heat flux into two different plane walls with the same thickness and the same temperature on the right face are shown for the same heat flux into each wall. So now we're looking at the thermal conductivity. So Q double prime is the same. And now what's different? Well, the temperature gradient is the same. And you remember Fourier's law. Well, if that dt, the numerator of this guy, if this is bigger, for the heat fluxes in both cases to be equal to one another, then that K will have to decrease proportionally, right? So bigger dt dx means lower K. And so that's the case with wall 1. So wall wall um, wall wall 1 has a bigger dTdx, a smaller K value. So wall 2 has a higher K value, higher thermal conductivity than wall 1. All right. So similarly speaking, now the only difference here is that we have a negative Q, but it doesn't matter, right? It's the same. We're looking at Fourier's law, looking at the dt dx, the steepness of that slope, and the steeper that slope is, if those heat fluxes are the same, the steeper that heat flux is for one, the K value has to be lower, right? So wall 1 has a higher thermal conductivity than wall 2. Question 11, this is asking about the one-dimensional temperature distribution in the plane wall. So that dt dx would be the T2 minus T1, right? T at x equals L minus T1, and so you can see that that would be a negative number. Question 2, temperature distribution in a plane wall at an instant in time is, well, is shown, and then we are looking at the left face at x equals 0, and we're asking about heat transfer. So Q is going to go in the direction of decreasing temperature, so it's obviously going from the right to the left, and this looks like the same scenario that we see in figure 3.10a. All right, question 13. Again, it looks like we might have an endothermic reaction. So Q dot would maybe be a negative number, pulling that temperature down in the middle. But we don't really care what's going on there. We just care about what's going on at x equals L, and we want to know about the heat flux. And Q goes in the direction of decreasing temperature, so it's going to go from the right to the left, right into the wall. So the answer is D. Question 14, you've got a steady state temperature distribution in a wall with thermal conductivity that varies with position is shown. So the correct statement about thermal conductivity of the wall is, so let's just see, is A possible? Is it constant, right? Which has kind of been our mode of operation from the get-go, that K is equal to some constant value, and it doesn't depend on position. But let's just, for the sake of this problem, let's see if that's possible in this case with that temperature profile. So equation 2.19 from your book is that heat diffusion equation right before we make the assumption that K is equal to 0 and then divide all the way through. So let's start with that, and it's one-dimensional, so we can get rid of a couple of terms. We can get rid of that last term because it's steady state. There's no indication that there's any heat generation, so let's go ahead and get rid of that. And so all we're left with is dx of k dt dx is equal to 0. And if I integrate that, I could see that the value of k dt dx is equal to some constant. And so if that product is equal to a constant, well, let's look at our temperature distribution. So dt dx, remember, that's the slope. So dt dx is clearly not a constant from 0 to L. And so K cannot be a constant from 0 to L, because how else would the products of two non-constants be some constant? So it can't be A. But what it is, you could see that if that value, K dt dx, if it's equal to a constant, as dt dx goes up, K will have to go down to compensate. So you can see at x equals 0, like towards the left, the slope dt dx is bigger, and so the K is going to be smaller. But as you go up in x, the slope gets a little bit more flattened out, so dt dx goes down and K goes up, so it increases in the x direction. Question 15, so we got a plain wall exposed to a hot environment. The right-hand side is insulated, and there's no heat generation, no nothing going on. There's really nothing to cause any of the scenarios that we see in A, B, or D, right? If nothing is going on to create a temperature gradient within that medium and everything has reached steady state conditions, this means that the wall is at some constant temperature, which isn't terribly interesting, right? This is clearly not question 165. I think this is question 16. But we've got a composite wall composed of two layers, each with constant properties. Thermal conductivity of layer 1 is twice that of layer 2. So for steady state conditions through the wall with no thermal heat generation, we're looking for the correct temperature distribution. So I know Q is constant through the whole thing. So if I look at, there we go. Well, let's start right here. So if I apply my heat diffusion equation, steady state, no heat generation, one dimensional, um, assuming K is constant, right, within one particular section, right, within either material 1 or 2, we eventually get that the slope dt dx is equal to some constant c1 over k. So if the K value is bigger, as it is for material 1, then your dt dx is going to be smaller. It's going to be less steep. And so that's the case for part D. Now, question 17 is just the opposite, right? Same idea, except now K1 is smaller than K2, and so dt dx is going to, if your K value is less, then your dt dx is going to be bigger, right? So that's going to be the case in case 1. You'll have a steeper slope than in material 2. Question 18, we have steady state heat transfer occurs through a wall of the hollow cylinder as shown. There's no internal heat generation. And so we want to relate the heat flux, look at the heat flux to the inner surface. We want to know how that relates to the outer surface. Well, you could absolutely say that if I did an energy balance, I get rid of, it's steady state, so the E dot ST goes away. There's no heat generation. So all I've got is the E dot in and the E dot out. So you could absolutely say that the heat transfer rates at each of those radii are equal to one another at the inner radius and the outer radius. But as far as flux, right, if I put those in terms of flux, well, I can see that that's absolutely going to change things. And the flux at the inner surface is going to be less than the heat flux at the outer surface, right? Yeah. So, okay, there we go. Wait, did I do that wrong? I said less. So R over R, yeah. What did I say? I feel like I said that wrong. Yeah, because QR is going to be a factor of R over little r, bigger than the Q flux at the outer radius. So yeah. All right, question 19. So this is on fins. A fin is used to transfer heat from a warm surface to colder air if the base temperature is decreased and all the other parameters remain the same, the heat transfer rate from the fin. And the answer here is it decreases. So very simply, a smaller delta T just means that you have lower heat transfer rate, right? All right, question 20. A fin is used to transfer heat from a warm surface to colder air if the thermal conductivity of the fin is increased and all the other parameters remain the same. The heat transfer rate from the fin, well, it's going to increase, right? K goes up, faster heat transfer rate. Question 21. A fin is used to transfer heat from a warm surface to a colder air. If the fin length is increased and all other parameters remain the same, the fin efficiency. So the fin efficiency is related to the heat transfer rate. It's the heat transfer rate over the maximum possible heat transfer rate. And so if we look at table 3.4, which is on your equation sheet, and I look at the heat transfer rate Q, and if you watch the video, you know that most of the time, so case A and case B, case A is the most complex model for a fin. Case B is good enough for us, okay? So good enough for us, right? And then case C and case D are very specific conditions. But case B is typically what you're going to be using, right? So the heat transfer rate, it's this big M times the hyperbolic tangent times ML. So L is what we're looking at increasing. And if I look at the function hyperbolic tangent of x, right? So hyperbolic tangent of ml, as ml increases, then that q is also going to increase. That hyperbolic tangent is also going to increase. So as L increases, so does the heat transfer rate. All right. And then Q21, question 21. I think this is the last question. So as a fin transfers heat from a warm wall at TB to the surrounding air at T infinity. The figure that best describes the temperature distribution in the film, and this is straight from the video. And so the temperature, as you move away from that hot base, right, it will come closer and closer into equilibrium with the convective environment, right? And as a side note, as that occurs, as you move down, as you move away from the base, that heat transfer rate is also that delta T is going to go down, and so the heat transfer rate is going to go down as well. Okay, so I think that's it. So good luck on your test. And if you have questions, I'll have office hours today, and Riley will have them as well um, today, Thursday morning, or Thursday, and then Friday as well. If you, okay, all right, thank you.